Alright, so this is the Thermodynamics 2 at the South Dakota School of Mines and Technology. Homework solutions. This is homework number 8, which is on reaction equilibrium. We're still in problem number 1, but this is part C. In problem number 1, what you have is you have these different reactions, and this is a problem from the final exam. And you're trying to figure out how to solve a quote-unquote problem. The temperature's too high, the pressure's too high. And again, it's asking you to do like one of 3 things and decide, okay, which one's the best one to do. And it's not like you're changing the pressure of a reactor. What you're doing is or removing water or something. What you're doing is you're changing the reactor setup so that it will achieve the problem that you're trying to achieve. Okay. In this case, I have hydrogen fluoride. That's capital F. I have hydrogen fluoride and silica, aqueous silica, and it's going to this crazy thing in water, liquid water, not vaporous water. Okay. Essentially, that's kind of precipitating out in a sense. Okay. The problem is I want to eliminate as much HF gas as possible. Why? Well, HF gas is nasty. Okay, so I want to remove as much HF gas as possible, which means I run a really high extended reaction. Okay, so I want to extend the reaction to go as big as possible. Okay, I have 3 choices. I can increase my pressure. Okay, I can add alcohol as an inert. So maybe, like ethanol. But basically I'm adding a liquid inert. Or I can add more HF gas into the reactor. Okay. Hey, that might not be a bad idea because the more I feed in, the more I can get rid of, right? Not necessarily. Okay. Because I'm not focused on the HF, I'm focused on this guy. So the first thing I do every time, is I make sure my reaction is balanced. Well, I've got 1 H over here, I've got 4 H's it looks like, but I got 6 F's. So I definitely need at least 6 of these guys. Okay. Okay, I've got 1 silica. Let's see here, I have 6 hydrogens and 2 oxygens. I've got 4 hydrogens and 1 oxygen. Okay, if I make this a 2, okay, now I have 6 hydrogens and 2 oxygens. Alright, now I'm balanced, now I'm good to go. Okay, then I write out my equilibrium constant with respect to fugacity. So K equals pi times Fi hat over Fi naught to the new I. Now on the final, do you have to write this out? No, you just choose which one's the best. But it helps to write this out to get your mind on the right page, because you're not using Le Chatelier's principle, you're using fugacities. Alright, now, I got a heterogeneous reaction here. I got different phases, so I can't just assume ideal gas for everything. So I kind of got to go through this one by one. Okay, so hydrogen fluoride is a gas. What's the fugacity of a gas? That is Y. Now let's call this 1, we'll call this 2, we'll call this 3, we'll call this 4. Okay, that's Y1P to the new 1. What's the new of that guy? That's 6. So that's YIP to the 6. Alright. Oh, minus 6. Why is it minus 6? You're right, it is minus 6. Why is it minus 6? Because it's a reactant, that's right. Okay, Si2 aqueous, which basically means it's liquid. It's in the liquid phase, so I treat it as a liquid, okay, in terms of fugacities. I'm also going to assume, because it's aqueous, that this is an ideal solution. Okay. Just like I assume this is an ideal gas. Okay, and so an ideal solution, the fugacity, actually just boils down to X2, to its coefficient, which is minus 1. Okay, times, well that's a solid. What's the fugacity of a solid? Well, the fugacity of the solid is equal to the fugacity of the reference state for a solid. So it's just 1 to the 1. Okay. And then times the liquid, again, so I've got x4 to the 2. All right. And so this is going to simplify it down, and I want to extract out the total moles because I got an inert here. Okay. And so this is how it's going to look right now. I've got, let's see here, I've got N4 over N total squared, all over, well really, it's always the kind of the moles, so I got N, let's write it this way, N4 squared over N1 to the 6th times N2. Okay. Now it's not just P to the nu and N total to the nu. Why not? Because I have different phases. So it's more P to the nu of the vapor over N total to the nu of the vapor times N total to the nu of the liquid. Okay. So what's the nu of the vapor? It's just minus 6. Okay. What is the nu of the liquid? Well, I've got 2 minus 1, so it's 1. Okay. And so I've got here N4 squared. I said it was minus 1, right? No, I said it was 1. So it's trying to trick you. It's minus 6 for that guy. So I got N total of the vapor to the 6th, vapor liquid, all over N1 to the 6th times N2 times N total of the liquid, so the liquid is 1, over P to the 6th. Okay, that is a nasty thing, but you know what? I simplified it down. Should be easy enough to manipulate. Now, okay, I want extended reaction to be as high as possible. So basically, I want my reactants, I want my reactants to be low and my products to be high. Okay, and this is all equal to K, obviously. All right. Well, what's happening to K? K is constant. K is a constant, K is a constant, K is a constant. So I'm not, if I do these things, I'm not changing K, I'm changing the extended reaction. Alright, so now that we got that off my chest, how do I increase extended reaction? Let's look at pressure. Okay, well, what does pressure affect? Pressure affects the pressure. Okay, and so I rearrange this essentially. So I got P to the 6th equals products over reactants, and I got some other stuff in there. Okay, increase P. So if I increase P, what is this overall increase? Yeah, because this, it's P to the 6th. So if I go from 1 to the 6th to 2 to the 6th, I definitely increase. Okay, so my products over my reactants increases. Is that a good or a bad thing? It's a good thing, because I want my extended reaction to be high. So this is a good thing. Is it the most good thing? I don't know yet. But I know it's a good thing. All right, let's move on to the next one. Now, why? Because nu is greater than 0. Okay, sorry, less than 0. Nu of the vapor is less than 0. So, nu of the vapor is less than 0. All right. I've got a liquid inert. Okay. So I don't affect this guy, but I do affect this guy. So, no, yes. Okay, so if I move that over, I have NT liquid equals products over reactants. Okay, so I increase the total moles of the liquid by adding an inert. Is that a good or a bad thing? It's also a good thing because it's going to make my products go up. Which one's better? Well, I'll come back to that later. But I know it's a good thing. All right. Let's look at the last one. Hydrogen fluoride. All right. So that's, let's see here, N1. Okay, so in that case, I got N1 to the 6th equals, products over reactants times stuff. Okay. Okay, so I'm increasing that one. Is that a good or a bad thing? It's a good thing, yeah. Well, they're all good. So really, I mean, in reality, I should do all three. But if I have to choose between one, maybe there's a cost issue, and I only can do one of these. Which one should I do? In what order should I do these? Okay, maybe I can't just change the pressure. Maybe I can't just add alcohol. I have to kind of do these things in stages. Okay, and again, it's not like I'm just adding alcohol. It's not like I have a reactor and boom, I add some alcohol. No, I figure out how to rewire my whole reacting system to make sure that alcohol's in the system. Okay, so I have to figure out which one's the best. And this is where real numbers help. Okay? This is where real numbers help. So in a sense, because my 3's not in here, I'm just trying to make N4 as big as possible. Okay? So that's what I'm really focused on. So let's rearrange this so it's like, equals N4, so to speak. Okay? This notebook will be something. Alright. So I've got constants. Okay, so I've got p to the 6th times n1 to the 6th times n2 times n total of the liquid all over n total of the vapor to the 6th. And that all equals n4 squared. With, the k's in there too, but the k doesn't have any effect. Why? Because it's constant. All right. So if I kind of look at this again in real number sense, okay? So my base case is 2 squared, if everything's kind of starts out as 2. So 2 to the 6th times 2 to the 6th times 2, the total in the liquid. Well, if I have 2 in each one, okay, that's times 4, all over the total in the vapor, which is just 2 to the 6th. Okay. Okay, and then I'm going to one of 3 cases. Well, in this case, I'm going to 3 to the 6th. So, and I'm just trying to make this ratio as big as possible. Okay. And so I got, in this case, I got 3 to the 6th times 2 to the 6th times 2 times 4 over 2 to the 6th. So really I went from 2 to the 6th to 3 to the 6th. That's a pretty big change. All right, let's look at the next one. I introduced a inert in the liquid. So this 4 increases. So, and I increases by that 1. So I got 2 to the 6th times 2 to the 6th times 2 times 5 over 2 to the 6th. That increases it, but definitely not as much as this thing. Okay, so that can't be the highest. That's, okay. And then in the other case, okay, I'm adding fluorine, which affects how much fluorine, and it affects how much total vapor. So I got 3, I still got 2 to the 6th, because the pressure doesn't change, times 3 to the 6th times 2 times 4 over 3 to the 6th. Oh. Wait a second. That's not good. That's an indifferent. It doesn't matter what happens to hydrogen fluoride. Here I have 2 to the 6 times 2 times 4. Here I have 2 to the 6 times 2 times 4. I didn't do anything. So that's the worst one. Or rather, it's indifferent. But in terms of ranking them, it's the worst one. It's 3. It has to be. Okay. All right, well then that's easy. I can just look at these and be like, oh, well that's 3 to the 6, that's just 1. And so this one's easily the best, and this one's easily in the middle. Again, the y, because the nu is, minus 6. It's so huge. Here, the nu of the vapor, the nu of the liquid reaction is so much smaller than the nu of the vapor reaction. Okay. And then on that bottom, it's indifferent because it's the only gas in the system. And so it doesn't change the mole fraction. And it has no effect. Okay. But again, to kind of summarize, how do I approach these problems? Balance the reaction, write out K, and move things around with real numbers to see what's going on.